we were doing work integrals. We're doing work integrals, and often there's an easier way to do work integrals uh, when this is the case, when f, your vector field, is conservative. Remember, this was the work integral. F is a vector field, and this is what it means to be conservative. It means your vector field is the gradient of some differentiable scalar function phi that we call phi the potential function. When that is the case, this work integral just becomes the phi evaluated at where the path stopped minus where the path started. Remember what a work integral is. It's an integral through a vector field over a curve or path. So that means we don't care what the path does between its endpoints. All it matters is where it starts and where it stops. And we don't even have to take an integral. We don't even have to evaluate an integral the normal way. Two tricky parts to the whole thing. One is, how do you know it's conservative? How do you know the vector field is conservative? And secondly, how do you find phi, the potential function? Anyway, because it does depend on what the path took. It's called path independence. Well, there's two ways to find out if it's conservative. One is if you can find the phi such that its gradient equals the vector field. The other way is if the curl is 0. And if it's only a 2D vector field, two-dimensional vector field, the curl amounts to just this. These two partials are equal to each other. Partial of p with respect to y equals partial of q with respect to x. Well, let's go through an example. I'll call it the long, slow, sure way. Here's the problem. Evaluate this integral. Hopefully, from the previous video, you know that this is a work integral, right? It's only a single integral symbol, but it's got a dx, dy, dz in it. It's a work integral. This kind of gives it away because it doesn't even give you the path. It just gives you the endpoints. So first, let's see if it is conservative. And hopefully you can now pick out what f is in vector format. E to the 2z, 3y squared, 2x e to the 2z. So those are my p, q's, and r. P, q, r. Take the curl. Set up this determinant, right? We did that in a previous video. See this guy? There's no y here, that's a 0. This guy, no c in this, that's a 0. This will be 2 e to the 2z minus e to the 2z. 2 e to the 2z. And the last one, 0 minus 0. Anyway, but yes, lo and behold, the whole thing is 0. Therefore, it is conservative. That means there is a potential function such that its gradient equals f. That means this. So let's see. We have this statement, the true statement, right? Because it's because we said it's conservative. Well, let me go through how to find phi the slow, sure way. It's called partial integration. Look at this equation. It means the partial of f, partial of phi with respect to x, e to the 2z. See what that means. Multiply through by partial of x. Get the partial of phi equals e to the 2z partial of x. Integrate both. When I integrate partial of phi, I just get phi. When I integrate this guy, it's a partial integration with respect to x. There's no x in e to the 2z. So this guy is just going to be x e to the 2z. guess I skipped a step. I can go from here to there just by integrating both sides. And this left side is just the integral of a derivative, so it's just a phi. This is just going to be x e to the 2z. And I have to add a constant of integration. But this is partial integration, so that constant is really a function of the remaining variables. And at this point, those remaining variables are y and z. All right? That's one step. So the next thing says partial of phi with respect to y equals 3y squared. Partial of phi with respect to y equals 3y squared. But here's what phi was. It's partial with respect to y. There's no y in this thing, so that's a 0. And this will just be the partial of g with respect to y. Do the same kind of trick, multiply through by partial y, take the integral of both sides. Got that. This guy will just be g. And this will be y cubed. Plus a constant of integration, which is now just a function of just a one remaining variable, z. So that's what this g was. P at this point is x e to the 2z plus y cubed plus h. So now you do the third equation. Partial phi with respect to z equals this, 2x e to the 2z. And what is the partial phi with respect to z? Here was phi, so we're going to have 2x e to the 2z plus 0 plus the partial of h with respect to z. These guys cancel, and I just have the partial of h equals 0, which means it's a constant. At this point, we just set it to 0. Won't really matter if we set it to something else. So it's easy just to set it to 0. So that's what h was. Here's where we were. H is 0, so here's what our total phi is. And at this point, it's always a good idea to check and see if it makes sense. Let's take this guy's gradient. You'll get this, and lo and behold, that is our vector field. Yes, that phi works. Now what do? Here was the integral we needed to take. Now all we need to do is evaluate that phi at the two endpoints. Here was the phi. Here's the two endpoints. X2, Y2 is log 3. 2 e to the 2 log 3 plus 2 cubed minus this guy. Get your start and stop, or stop and start sign correctly. It's where you end minus where you started. So it would be minus x is 1, y is 1, z is still log 3. So subtract off 1 e to the 2 log 3, 1 cubed. E to the 2 log 3, there's just a little bit of algebra. E to the 2 log 3, well, 2 log 3 is log 3 squared, which is log 9, and e to the log something is just the sum. So that's where you get this thing is a 9. The rest of it's arithmetic and you can answer it. There's something I call the easy way. If you can just find a phi and then check it, and its gradient equals f, you don't have to find the curl. And let's see if there's an easy way to find the phi. Here we're doing the same problem. We've got the same f. What you do is just you take the integral of p, q, and r, each respectively with respect to x, y, and z, and then add them up without repetitions. So here's p. P is e to the 2z. Integrate that with respect to x, you get x e to the 2z. Q is 3y squared. Integrate that with respect to y, you get y cubed. Q is 2x e to the 2z. Integrate that with respect to z, you get x e to the 2z. That's the same as we got from x. We have a repeated term. So we don't repeat it in the answer. So the phi, the potential phi, or the maybe phi, is x e to the 2z plus y cubed. But now when you do it this way, you have to actually check. It's possible to go through all this stuff and get a phi. Phi's gradient does not equal f. You use the easy way, you actually do have to check. Not just a good idea. We really need to do it. And lo and behold, it does equal the vector field. After that, it's the same as we did before. We'll evaluate the answer the same. That's the basic. I'll do more examples in subsequent